And yeah, I guess it's 4 p.m. Central European time, so it's time of webinar. We have to start. We have about 130 participants now, and yeah, let's start with introduction. So my name is Victor Brovkin. I lead a group in MPI for meteorology in Hamburg, and I'm a member of a tipping point working group in AIMS. I will tell about AIMS later. I would like to welcome everyone to this third webinar in the discussion series on tipping elements, irreversibility, and abrupt changes in the off system. And I moderate the meeting today with Claire Creed. So Claire is an expert in the permafrost carbon and methane, and she leads a group in Alfred Wegener Institute in Potsdam, Germany. Just to remind you, the goal of this discussion series is to advance knowledge on tipping elements, facilitate the analysis in the scientific community, develop a research agenda for tipping points, and design joint experiments and ideas for a tipping element model intercomparison project called TIPMIP. The first seminar in this series started in September last year, and it provided an overview of tipping elements and climate extremes. It can be found on the WCRP YouTube channel. The next webinar will take place next week and will focus on ice sheets. You can register using the link in the chat box. I hope that Caroline will put a link there. The focus for today is on permafrost tipping points, and we will hear presentations on observations of permafrost physics, carbon feedback, and potential tipping of the permafrost. Before going into introduction of the speakers, I want to say a few words about three organizations which have initiated this discussion series. Firstly, the Earth Commission. It is a global team of scientists with a mission to define a safe and just corridor for people and planet. This will inform setting targets for a stable and safe planet, and will help us developing and understanding pathways that are compatible with these targets. Secondly, the analysis, integration, and modeling of the Earth system. AIMS project is a global research network of future Earth, comprised of Earth system scientists and scholars developing interdisciplinary ways to understand complexity of a natural world and its interaction with human activities. Last but not least, the Safe Landing Climate Lighthouse activity of the World Climate Research Program, WCRP, explore routes to safe landing spaces for human and natural system. It explores future pathway that avoids dangerous climate change, while at the same time contributes to the United Nations Sustainable Development Goals, SDGs. Few words on the house rules. During our speaker talks, feel free to pose questions using the Q&A feature at the bottom of the Zoom window. We will get to this question in a discussion session following the presentation, so not after the first presentation. We allocated a lot of time for discussion at the end. Please feel free to make comments in the chat box and in the Miro board through the link in the chat box. We also have a number of experts in the audience and encourage a lot of interactions. The Miro board will be kept open throughout the week for any ongoing discussion. The webinar is recorded. Again, reminder, we will post the recording on the WCRP YouTube channel, and it will be accessible in the future. Now about our speakers. It is my pleasure to introduce our first speaker, Professor Hanne Christiansen. Hanne is professor in physical geography and new Arctic chair in permafrost, as well as past president of the International Permafrost Association, IPA. Her main research topic is periglacial geomorphology. We focus on permafrost and its climatic control. Hanne was leading the IPI Thermal State of Permafrost project internationally and in Norway, Svalbard. She is now involved in the permafrost part of the Svalbard Integrated Arctic Earth Observation System, SIOS, participating in the INFRA-NOR project. At the University Center in Svalbard, she leads the interdisciplinary scientific research project, developing a permafrost and meteorological climate change response system to build resilience in Arctic communities. Thank you, Hanne, for being here, and now the floor is yours.
Thank you, Victor. we will see if this works. Hopefully you see, oh, we'll try one more time. So hopefully you see my presentation now.
Yes.
So I'm very thankful that you wanted to invite me to actually talk about permafrost and climate change and what we are observing. I will take you to Svalbard, and obviously this is where I live. This is where I've been spending the last 20 years. And so today I'm going to focus on that. But first, of course, we're going to talk about what is permafrost. So permafrost is defined as ground that is at or below 0 degrees for at least 2 consecutive years. And it's very important to remember that the ground can be rock, it can be sediment, it can be organic material, but it's everything below the ground surface. And when you're looking at a landscape, a periglacial landscape like the one you're looking into here, you maybe don't think so very much about permafrost, but actually permafrost is a major component of the periglacial landscape. And therefore, of course, it's very important to understand what kind of changes can happen if the permafrost is affected. How can it affect the landscape stability? There are many different landforms. Generally, when you look at a landscape like this, you maybe don't see them. So my mission today is to take you to Svalbard for some examples of some of these landscapes and try to dive into at least 3 permafrost-dependent landforms that really is affected by climatic change. But before we do that, I'm also going to give you a little bit basics in permafrost and talk about the climate essential variables that we have for permafrost, the permafrost temperature, the observations that we have, but also the active layer thickness. And finally, finish off with some ambitions of what we are actually doing right now when it comes to not just doing science, but also doing science that is directly useful for recording and observing abrupt changes in the climate system that affects the permafrost and how we do that on Svalbard. So that's what I look forward to talking to you about today. Obviously, the extent of permafrost is a very important one. So permafrost is occurring in 20 to 25% of the terrestrial parts of planet Earth. Those are the colored ones that you see here. You're looking at one of the recent published permafrost maps, which shows you these things. You can also see that there are different types of permafrost. When we come closer to the Arctic central area, we of course have continuous permafrost. This means that we have around 90% of the landscape has permafrost. And if you move towards the southern fringe, those areas that has not such a strong color, you only have between maybe 0 and 10% permafrost. So we don't have permafrost everywhere in the colored areas that you're seeing here. And another important thing to observe when you're looking at this map is, of course, the asymmetrical distribution. Being from Europe, you'll be immediately noticing that there's kind of something missing in Europe. We don't have as much permafrost in Europe at the same latitude as we do have in North America and Russia. And this is, of course, the climate system controlling that. So the inflow of warm water through the North Atlantic is actually controlling the extent of permafrost that way. So we've looked at the types of permafrost this way. If we then think about stability of permafrost is of course very important in this connection. And if we move back in time into what we would normally call the late permafrost maximum, at the time when the glaciers were last big, and that's 17,000 years back in time during the last glaciation. When you're looking at a map with the same kind of configuration, you can see that the purple areas or pink areas is where we have the glacial coverage at that time. But you can also see the blue areas here. And that is where we have from reconstruction knowledge about the existence of permafrost. So basically, when you're looking at this map here, we can see that permafrost has been extending all the way to the Mediterranean Sea in Europe. And even large areas in Asia has also had permafrost that doesn't have permafrost presently. When we're going into Siberia, this is an area that wasn't covered with glaciers during the last glaciation, and therefore the permafrost is very thick and very extensive over there. You can see areas or meet areas in Siberia that has permafrost with a thickness more than 1 kilometer. And this is reflecting these long periods of time where we had cooling of the ground. Actually, recently, new research from one of these big scars made into the permafrost of Siberia has shown permafrost ages of more than 500,000, 650,000 years. So this is showing that permafrost can actually survive interglacial periods. So that's important to have in the back of our mind when talking about permafrost and change, that given the right cover, then you can still preserve permafrost. And when we're talking about permafrost and climate change, it's the top of the permafrost that's most interesting. So how do we actually investigate the permafrost and what do we find out? This is one of the most important instruments that I use. And this is our permafrost drill rig that you see in the mountaintop in Svalbard, because what we need to do is that we need to get into the permafrost. So what we do is that we drill boreholes where we have possibilities for recording the temperature, but where we also have possibilities for actually seeing what is inside the permafrost. And you can see that people, when they're working on these things, they get very happy when they get these cores out of the ground. And what you're looking at is a core from sedimentary infield valley, but also a core from a combination of rock and ice. And this is some of the challenges we have at the moment, is to actually obtain cores from different types and different landforms. And that's what we are focusing some of our research on in Svalbard, trying to understand how do we do this the best possible way, because we need this knowledge. I'll just share with you also this photo, because then you're able to see how permafrost, what it's actually consisting of. On the photo, you see a centimeter scale, and then you see also the ice layers in such a permafrost core. That's the dark, the gray part. And you can see that this is actually a slide from a core from Atvendalen in Svalbard, that we have quite ice-rich sedimentary ground. And we need this knowledge, because if we thaw the top of the permafrost, obviously the ice will turn into water, so there will be this phase change, and we'll get rid of that part of the ground, so the ground will subside. And also, this phase change takes time. So when we're looking into recording with temperature, the permafrost changes, it's important to know what's into the ground. Presently, we have maybe around 800 or 1,000 boreholes that is recording temperature and sharing data from various periods of time. But from very few of them do we actually have very good records of what is inside the permafrost. So this is also something that we really need to have. When we then have our permafrost borehole, you see the top of a borehole coming out of the ground here in Atvendalen as well in Svalbard. We then start instrumenting them and being able to record the ground thermal regime that you're looking at on this slide to the right part here. And there you can see that in the top of the ground, we have what we call the active layer, and below that, the permafrost. The active layer is that part of the ground that experiences the warmest temperature in summer and coldest in winter. And this is why the ground thaws to a certain depth, which is what we call the active layer. And then we proceed down into the permafrost. And you'll be able to see a point approximately here, which we call the zero annual amplitude. So that's the depth to which we have the atmospheric variability on an annual basis reflected in the permafrost. That means that below that part, we actually going into seeing the long-term permafrost temperature. Unfortunately, again, not many boreholes really extend very far down into the ground and recording that, but some do. And if you look into this publication, which actually came out last week, it gives you the possibility to see how change is happening recently in permafrost, or actually over the observation period. The size of the round circles is indicating the amount of warming, and you'll be able to see that warming rate is up to 1 degree per decade, reflected this way. And you're also able to see that the largest warming is going on in the high Arctic areas. In the same publication, you also have this figure, which shows you the temperature change. And you can see that there's not a lot of boreholes that has a very long record, but we do have some boreholes that started recording temperatures in the late 1970s, early 80s, and then of course more coming after that. But we do not have very many very long records. And the important thing to notice about the left part of the figure is that these changes that this paper records is actually from below the depth of zero annual amplitude. So we're looking into the longer term permafrost trends this way. If you look at Svalbard, you will be able to see that this is one of the plots where we do have a large change. So I would now like to take you to Svalbard and share with you the details from one of these sites. And then it's looking like this. There you can see that we have since 2008, 2009, during the International Polar Year, drilled borehole that is almost 30 meters down deep and recorded the ground thermal profile. And you can see how that has changed between 2008-9 and until 17-18, which was among the warmest years we've had so far recorded in this borehole. And there you can see that if you go down to 20 meters, we have a change of around 0.6 degrees per decade. And you have the temperature series over here. So you can see these warmest year, 2018-19, around there, and then a decrease since then. If we then move on to the other ECV, the other permafrost essential climate variable, which is the active layer thickness. There are different ways to measure that, but generally what we try to do is to do probing, which is what you see done on the photo here. And this typically happens in grids. And so you report averages of typically 121 points in these grids with grid sizes of 10 meters, 100 meters. But of course, that technique you can only use if you can actually penetrate the ground. And you cannot do that if you have coarse-grained material or even if you're measuring in bedrock. And therefore, some of the observations that is being reported comes from individual boreholes, where you then interpolate between the semesters in boreholes. From Svalbard, the record looked like this. In the year 2000, we actually started doing a grid in the Adventine Valley, and you can see how this change has been up to around 1 centimeter per year in the first 10, 15 years, and then there's a slight decrease recently. We also started another grid over the ice wedges, which I'll return to talking about the landforms a little bit later. But that didn't show any trend, so you can try to keep that in mind as well. But if we go into the complete Arctic, obviously it's also important to have an overview of that. And then you can see that Svalbard is representing one of the sites which has a relatively large active layer. Here you're looking at the centimeter active layer thickness over the entire Arctic in many different regions, but only from sites that actually have 10 years of data. You can also see that Northwest Russia and Siberia, relatively thick active layers. And then of course the change is interesting. And if you're looking at the entire period 1990 to 2018, you can see that at least one site has recorded a change of almost 3-4 centimeters per year. And whereas other sites in general, it's 1 to 2 centimeters. Generally, I would say that, of course, the evidence is so that you have the thickest increase. You also saw that from Svalbard when you're dealing with bedrock. It's more conductive, and therefore you can have larger change. Whereas many of these sites are from the CARM network, which builds on grids, and therefore they are typically in sediments that doesn't react as quickly as the bedrock does. From the Nordic area in general, I also wanted to highlight a little bit what we figured out here, because we have this quite large climate sensitivity from permafrost due to the climate system, as I explained on the map. We can also see that reflected in the active layer thicknesses. So here you're looking at data from both northern Sweden, the Abisko sites, which were actually started back in 1978. And you can see the increase in active layer thickness there. Then there's 2 sites from Sakenberg in Northeast Greenland. That's the Zerocam 1 and Zerocam 2, 1996 and onwards, also showing the increase, and the Uniscam site that I showed you from Adventdalen as well. And what we've done there has been basically to try to test the fact that most of us normally know is that the active layer is dependent on the amount of summer energy being provided to the ground, reflected in the thawing degree days. So both of the continental parts of the Nordic area, both Abisko, but also Sakenberg, they have a relationship between active layer thickness and the square root of the thawing degree days. That is not the case in Svalbard. And that's basically because Svalbard is extremely maritime and the summers doesn't change very much. So we see more of an influence on the winter conditions directly also on active layer in Svalbard. So that is also why a widespread monitoring network is important to be able to address how different parts of the world react this way. Where do we find data? I can't show you all the data in any way in this talk, but I would like you to know that the Global Terrestrial Network for Permafrost is really where you are able to find data. This has both the permafrost ECVs, so the permafrost temperature and the active layer thickness. And then, of course, there are many regional and national databases, platforms, even institutional ones. In Svalbard, we have the SIAS one, Svalbard Integrated Arctic Earth Observing System, which has core data that everyone that works in that system has to report to SIAS. In Switzerland, there's Permafrost. There are many examples of this where you can actually find and have access to data. And then very exciting is that we are maybe looking into getting a new permafrost ECV, thanks to the work in the European Space Agency Climate Initiative on permafrost, and also the work in the International Permafrost Association's work group on rock glaciers. They have for years now been suggesting to try to include the rock glacier dynamics or kinematics as another permafrost ECV. And this takes me into talking about permafrost landforms and their dynamics and what we know about that and why they are important. So rock glacier dynamics is, as you just heard, one of the most important parameters when we are talking about permafrost in high relief, so mountain areas. You're looking at a photograph here where you can see there's like a terrace form sitting here, and that's a rock glacier. They can typically be 10, 20, 30, 40 meters thick, and then they can be, several hundred meters long, and also detaching from the mountainside like that. And that is because they consist of mixtures of rock and ice that deforms under gravity, and then kind of moves the talus slope away from the mountainside. So of course, it's dependent on breakdown of rock on exposed free faces that we have in the mountains. And therefore, this is really one of the indicators that when you see a rock glacier, you know that permafrost is there. It can only exist if you have permafrost. And therefore, it's very nice that in this CCI Plus project, there's been now a set of observations from all over the world, actually, from mountains all over the world, to try to find out if it's possible to detect rock glaciers and their speed using INSAR remote sensing technology. And I can just tell you that about 10 minutes before we entered into this meeting, a paper was actually accepted into preprint in the Cryosphere, which is describing some of this work. It's also in some of the reports from the CCI Plus. But on the right-hand side, you see some of the data that we've done in Svalbard with this, where we actually mapped more than 200 rock glaciers, I think it's 260, moving objects, and been able to map the speed of their movement. And that's in centimeters to decimeter scale. And of course, interestingly, happening in areas where also people is living and infrastructure is sitting. So that's why this permafrost landform matters. If we move on to the lowland areas of permafrost areas, I'm sure many of you have flown over Arctic areas and seen these very beautiful polygonal ice fields or landforms that we typically call ice wedge polygons. That's also found in Atlant Island that you're looking at here. And if we were able to just dig into the ground, what you'll be able to see is a landform like this, where you actually have a wedge of ice. All this part here, the gray part, is basically ice that forms due to thermal contraction cracking of the ground, and then water running through the active layer into the permafrost, and thus the ice wedge growing, forming the pattern that we see here with low-centered ice wedge polygons. And then if the ice wedges undergo thermal erosion, if the climate is warming, the active layer thickening, the ice in the ice wedges will start to melt. And that would lead to flooding in the ice wedge troughs, not in the depressions in between. And so we start to disconnect the different troughs, and we have lakes over the ice wedges as the ice wedges degrade. And finally, we end up in a situation where we have high-centered polygons and fully drained landscapes. So we have a very large hydrological difference from these low-centered polygons to the fully connected and drained landscape in high-centered polygons. And that change has been pointed out in the Liljedahl et al. Paper already in 2016 as happening in most of the continental parts of the Arctic today. If we then go to Svalbard, we also looked into, or some people looked into this in Svalbard, and saw that if we look into aerial photographs from that part, we don't really see a big change. You have to remember that Svalbard is again maritime, so the summers doesn't change as much as they would do in continental areas. So we don't have a big change going on. If you look to the right part here, you can also see that we try to document that as well, because we take daily photos. I've done that since around 20 years of the ice wedge, and it's not showing any very big change. So what we've done with different colleagues is that we've instrumented these ice wedges completely so that we know the temperature, we know the expansion rate, we know how the ground is lifting and all of these things, and have been able to kind of conclude that even though what you're looking at here is increasing air temperatures, but also increasing ground surface temperatures and increasing top permafrost temperatures on an annual basis here, we still see cracking events. So this means that the ice wedge polygons are still active. And we found out that that's simply controlled by the fact that we still have cold spells in wintertime that drives the process. So again, digging deeper into the process is important to try to understand why don't we see the same thing all over in the Arctic. And then another beautiful permafrost landform that I'm sure many of you have actually seen in many lowland areas. In Svalbard, they are very dominant in the valleys, and these are pingos. And pingos are generally hills with an ice core. They can be 10, 20 meters high. They can be several hundred meters across. And in this valley, you can see one that is kind of in an initial stage here. You can see one that is in degraded stage. This means there's a lake in the middle part. There's one in the background connected to a glacier, and so on. So we observe them. We know they have a core of ice. We know they're quite important, but most of the time we don't really understand why are they important? What is controlling this? We know they come from pressurized water existing inside the permafrost. And again, in Atlant Island, we have quite many pingos. You can see that they are sitting all over the landscape like this. And some of my colleagues have actually been able to measure the amount of methane coming out in the water, dissolved in the water from these springs that's typically associated with the pingos. Some of the water makes it out and doesn't form ice. And that has led to the formation or the understanding that actually these pingos, they can act as direct sources where methane that is trapped below the permafrost can have access and come out through the permafrost, forming pingos on the surface. And this can be actually due to the fact that we earlier on maybe had pock marks. So this is biogenic, but also geogenic conditioned. It depends on what you have in the surface. But where we normally thought about permafrost as a seal, which kind of prevents anything from coming out, we can also see that we actually have permafrost with quite high emission rates coming out through these pingles. And finally, I want to just say a few words also about how we're trying, living in a place like what you're looking at here. You're looking at the capital in Svalbard, Longyearbyen. You can see that we have permafrost all over the area where we don't have glaciers, and we have infrastructure sitting almost on the mountain sides. So when we have rainstorms, and that is kind of an extreme event, you could call it. It's extreme in Svalbard when you have 20 millimeters of rain coming in one rainstorm, and the mean annual amount of precipitation is maybe 200 or 300 millimeters. Then it can trigger situations like this, where the entire active layer detaches. And actually this was going on over here and coming down here, crossing the roads and so on. And of course, we therefore have the aim that we will actually get all the permafrost observations that we have online. And this should be not just ground temperatures. It should also be what is the content of water in the active layer, so that if the active layer hasn't refrozen and we in the shoulder season starts to see more activity, then we're also able to observe this. So together with a lot of different colleagues from UNIS, but also from the local authorities and local companies, national institutions and companies, we are trying to do this now. And that is to be able to basically use our knowledge on what to do, where to do it, and then build a tool that will be online available to everyone interested, including the authorities that needs to decide what to do if sliding activity starts to happen. So with this, I better say thank you very much for your patience in listening to me. Thank you.
Thank you. Thank you very much, Hanne. That was really insightful, very insightful talk. Just remind everyone that if anyone has questions for Hanne, please post them in Q&R Zoom box or on the Miro board, and we will address them during the discussions session afterwards, after Gustaf's talk. And now I pass to Claire.
Yeah, thanks everybody for posting your questions so far to our question board. We're looking forward to answering those later. Now it's my pleasure to introduce Gustaf Hugelius, who is a senior lecturer in the Department of Physical Geography at Stockholm University. He's also the vice director of the Bolin Center of Climate Research and co-leads the research unit Landscape, Environment, and Geomatics. Gustaf is an expert in mapping permafrost soils and permafrost carbon, thanks to long periods spent in the field in both Siberia and Canada. So Gustaf, please start.
Thank you. Thank you very much, Claire. So can you see my screen okay? Yeah, great. Okay, so thank you for inviting me, and thank you all for coming to listen, and thank you very much, Hanne, for that excellent introduction to permafrost and all of the definitions and the physics behind it. I'm going to switch topic a little bit to talk more about the carbon feedback. So the title of my talk is the Permafrost Carbon Feedback and Potential Tipping Points. And I want to take the opportunity to acknowledge some co-authors that have contributed with knowledge and slides to this specific presentation: Sarah Chadburn, Jan Strauss, and Mary Turetsky. But also, of course, many others that have collaborated on the various findings over the years. So we're in a seminar series about tipping points. So I actually thought I would start with this very big picture graph from the latest IPCC report that emphasizes that so far we have a situation in the Earth system where every ton of CO2 added to the atmosphere basically linearly increases global warming. This graph shows you the cumulative CO2 emissions since the pre-industrial down here in gigatons of CO2 plotted against global warming. And this is still almost completely linear. And if we would have strong tipping elements in the Earth system being triggered, we might expect to see a trend, looking more like this. And actually, well, this is also what the warming would look like if we didn't have the strong terrestrial and oceanic sinks in the Earth system that actually absorb roughly half of the emitted CO2. So you could also, I tend to view, at least when talking about the permafrost carbon feedback or the feedbacks in these systems, more as a weakening of the already very strong terrestrial carbon sink. So it's really a part of those dynamics and part of the dynamics that so far, the Earth system has done us the favor of basically reabsorbing half of the CO2 we've emitted. But there are indications that the permafrost carbon feedback and other feedbacks might be pushing us in a direction where the warming actually deviates from the linear. So far, the model projections, you see different scenarios up to 2050 in this graph. Okay, so there might be a small indication that SSP 8.5 is slightly higher, and there are also indications that the natural sinks will actually weaken as we go into the future. But as of yet, we still have this linear relationship between what we emit and the warming that we observe in the atmosphere. So the topic here is the permafrost carbon feedback. This is a very simplified image of that, where we see global warming at the top, thawing permafrost. You see a very dramatic example of thawing permafrost. This is a head wall of a thaw slump developing in the Canadian Arctic. You have a permafrost professor for scale added down here. So you see the sort of massive scale of this particular landform. I like to use the image also because, I mean, most thawing permafrost is not this dramatic, but I think it's a good example of also the scale of the problem. We have huge areas of permafrost, very large amounts of carbon that is frozen in the permafrost, large amounts of ice and other things that can be impacted by the thaw. And what happens in a nutshell is that as the soil gets warmer, it thaws, more plant material that was previously protected in the sub-zero temperature, more old plant material is becoming remobilized, so that microbes, fungi and bacteria can start to eat these old plant remains, and as a byproduct of their respiration, they produce carbon dioxide and methane mainly, also nitrous oxide. And whether it comes out as CO2 or methane usually depends on the environmental condition of where the respiration takes place. If it's a wet, oxygen-free environment, you typically get a stronger methane flux, while if it's an aerated part of the soil, you typically get more CO2. Hanne showed you some very nice maps of the extent of permafrost. So you noted that it really covers a very large part of the Northern Hemisphere terrestrial system. And it actually includes a lot of subsea permafrost as well, but we're not getting so much into that. But in this, so it's not only a large area, it's also an area that hosts an enormous carbon pool. Then this is really the reason why, why the potential for the permafrost carbon feedback to affect the climate is so large, is simply because there's so much carbon frozen in permafrost. This is this bubble diagram shows all of the sizes of the bubbles here are proportional to the sizes of these individual carbon pools. The units are gigatons of carbon, so not gigatons of CO2, but gigatons of carbon or petagrams. And basically you see up here, you have the atmosphere, almost 900 petagrams and growing, vegetation, all living vegetation on Earth, a little bit more than 500 petagrams. And then if you add the global soils together, they are more than 3,000 petagrams. So by far the largest active carbon pool in the global carbon cycle. And out of these more than 3,000 petagrams or gigatons, roughly half are found in the permafrost region. So it's a disproportionately large carbon storage. It's about 15% of the soil area, but it stores almost half of the carbon. And out of this is 1,600 gigatons of permafrost region carbon, roughly 1,000 is really frozen. And the other 500-600 petagrams or gigatons are either in the active layer that thaws every summer that Hanne explained, or they might be in some parts of the landscape in the discontinuous permafrost zone where there's simply no permafrost at all. So as we showed you this zonation when we go south, that there are areas where there's a lot of large pockets of unfrozen terrain. But all of this carbon is still rather vulnerable to warming and can potentially be, or some parts of it can be remobilized under future climate warming. So then that leads us on to the big question of, are there really global scale permafrost tipping points? This was addressed in the most recent IPCC report as well. And they state this is adapted from box 5.1 in this report, that it's still unclear whether the permafrost carbon pool represents either a coherent global tipping element of the Earth system with a single abrupt threshold. So this is something that would be very alarming if there was really an abrupt threshold that could somehow trigger, the bulk of the permafrost carbon feedback. Or the other option is that it's a local scale tipping point without abrupt thresholds when aggregated across the Pan-Arctic region. And this is really what the observational evidence and global models results suggests. So basically, we don't see strong indications that there is this very finite threshold that when we cross that, we get a very rapid and strong shift of the whole system as such. It's a huge system that covers a large area, and there are a lot of local tipping points that we can cross, but not necessarily one that covers the full global scale or the Arctic scale of the permafrost. I'm not going to get so much show there are a lot of studies where you could dig into the references of what the models predict for Arctic scale permafrost extent relative to warming. I've chosen to highlight one particular study here by Chad Burnett al. Came out a couple of years ago. And this, if we go through this graph, what it shows us is permafrost remaining at future scenarios of global warming stabilization. So this is 0 degrees global warming. So that was before we started warming the Earth. This red box is the climate baseline of the 60s to the 90s. And then you have successively smaller areas of permafrost remaining at different levels of global stabilization temperatures. And these boxes represent basically observationally driven evidence. If we take our observations and best understanding of current distribution of permafrost in relation to temperature, that is what we get. The blue dots represent the different Earth system models from the EHSMIP 5 archive. So basically, the green line here shows us roughly what we see in the evidence, and the red line is one example of how a clear tipping point would look like. Then it would have perhaps a weaker decline, but then a sharp break. And there is no, at least global scale tipping point indicated by the models in the extent of permafrost as such. So, and I think, okay, so that can be seen as a positive thing, but I also think that when I think of tipping points, there's also this inherent, there's this threat, there's obviously the very strong threat of crossing that threshold, but there's also the inherent, perhaps false security of staying below the threshold, meaning that if we don't cross the tipping point, we're going to be okay. And I think that's the flip side of it, in that because we have this response, it's just a constant slippery slope. There's no threshold that we can just stay under and then we're fine. Every 1/10 of a degree matters, and every 1/10 of a degree thaws a lot of permafrost. So every degree of global warming, we lose about 4 million square kilometers of permafrost. And that has implications for the global climate and for many, many future generations that will come to soon. So at least, the current models and the current understanding would suggest that there's no Arctic or global scale tipping point that we can trigger like that. But with that said, there's very good understanding of strong local scale tipping points in the permafrost system. Now I'm calling this abrupt thaw. So, there are a lot of different terminologies, and Hanne showed you different examples of also similar processes. It's often also called thermokarst. But the key element to abrupt thaw or thermokarst, to this local scale strong shifts in the climate or in the landscape, in the permafrost landscape, is the occurrence of massive ground ice. So when you have a lot of massive ice in the ground, when that melts, drains away, you have this phase change that completely changes how the landscape looks. Now, these researchers here, they're looking at the upper right corner of an ice wedge. So one of these huge wedges of ice that is probably, it's roughly 10 meters wide and probably something around 30 meters deep or something like that. It's in a part of Siberia where as much as 70 to 80% of the ground volume is made out of pure ice. And what abrupt thaw does is that over time, the ice melts away, drains away, and then the whole ground surface settles and changes. So in this case, we have stable permafrost down here. This is a peatland, so it's a very different system from what we have over here. But when the ground ice, the ice core of this frozen peatland has disappeared, you're left with a lake instead. And of course, this is a tipping point locally that is very strong and is also at these policy timescales irreversible. And there are very many different various terrain types and landforms that are vulnerable to either gradual permafrost thaw. I mean, permafrost can also thaw without the presence of ground ice, and that still also yields greenhouse gas emissions. But many different landforms, different periglacial landforms respond differently and have different vulnerabilities to thaw, and they will emit different amounts of greenhouse gases following thaw. And there is, I would say, a very good observationally based understanding of these landforms. Scientists have been studying them for a long time. Even before scientists were aware of the very strong the carbon feedback to the global climate, there was still a large community of experts studying permafrost landforms. So we know a lot about permafrost landforms. We know quite a lot about the processes that cause, for instance, hill slope failure, thaw lake formation, or these peatland dynamics that give you different types of thermocost. There are also an emerging number of models that can, at least in quite simple ways, actually start to model these abrupt thaw events and how they might progress into the future. Those models are still not mature enough to really be, for instance, included in IPCC reports or similar, but still the knowledge is there and it's growing very fast. So this is a simplified schematic of what might happen. If you think of, these are the landforms that we get, what does that do to the climate or the carbon feedback of these areas? And here we start at the left, we have stable permafrost, and here we see it's also ice-rich permafrost. You have the active layer, you have the frozen ground with, I've drawn some ice wedges here. And typically stable permafrost is a net sink of CO2, so it pulls CO2 out to the atmosphere, and it's often neutral when it comes to the methane balance. This, of course, varies, and if it's a wet area, it might not be neutral, etc. But in this particular case, it's a dry upland tundra that is typically neutral. But on the long term, it's still cooling the climate, and this is what most of the Arctic is still doing across much of the intact permafrost areas. As permafrost warms and starts to degrade, we see initial loss of ground ice, the active layer deepens, and then we actually get a source of CO2 instead. The methane balance can still be neutral, but then we cross this abrupt thaw collapse where we lose so much ground ice that you get a completely different system. It's a lake. The permafrost is completely gone, and now we're left with a system that's both a strong CO2 sink and a strong methane sink. And when it comes to this abrupt thaw landforms, the methane is actually usually the greenhouse gas that, at least on the short term, drives the strongest response, at least for the lake and the peatland areas, not necessarily for the hill slope thermokarst where the CO2 fluxes still are the strongest radiative source. One thing that I'm not showing you in this graph, but that is very important in this context, is that actually if you wait a little bit more, you will actually get the system where the methane flux will start to go down again. The CO2 will also shift from a source back to a sink as the ecosystem reestablishes. And over a long time, this will become a net sink that actually cools the climate again. But that is something that takes centuries to even millennia, depending on the landform. So you also need this long-term time perspective on this landform to really try to incorporate it into models and to our understanding of the climate feedbacks. And also I've talked about abrupt thaw as something that is coming, but it's also something that is really happening already. There's strong observational evidence of increases in abrupt thaw rates. This is an example of a 60-fold increase observed in abrupt hill slope thaw failure in the Canadian high Arctic over 30 years. And these are areas with really cold permafrost. So, but even in those areas with really cold permafrost, these landforms are really growing, and in some cases quite rapidly. Another example from the Canadian high Arctic. This is again in very cold permafrost, where a succession of unusually warm summers, not the last few summers, but actually an earlier heat wave that was more regional to the Canadian Arctic, triggered a massive abrupt thaw in areas that, according to models, should have been stable for at least another 70 years. But just a few unusually warm summers started triggering thermokarst events, and you see a completely different ecosystem in the exact same site. And if we take the gradual permafrost thaw that happens everywhere, and we combine that with the abrupt thaw, we actually get a relatively strong global warming, sort of combined global warming signal. So now there it goes. So in this graph combines the abrupt thaw emissions with the IPCC-based emissions of mainly of gradual thaw. And here you see sort of gigatons of CO2 emitted from permafrost until the year 2100 under different scenarios of global warming. And the black dots are the gradual thaw, and the purple dots are if you add abrupt thaw, based on a publication by Turetsky and colleagues that came out in 2020. And you see that this actually significantly adds to the radiative forcing of the permafrost thaw. So this is something that, you know, they are local tipping points, but if you add all of these local tipping points up, it really gives you a gradual strong increase across the full Arctic. So it doesn't have a threshold behavior at the Arctic scale, but locally it's a threshold that scaled up gives you a strong linear or even exponential increase over short times in the warming. Another important concept to talk about when you're discussing, you know, strong responses or something similar to tipping points is overshoot warming and permafrost thaw. Overshoot warming is this concept where we might allow countries to keep emit CO2 for a bit longer and then use negative emissions to pull the emissions back down. So two different ways of reaching a target temperature: the sort of way of very rapid emission reductions to reach target temperatures directly, or the other way where we keep emitting for a few more decades and then trust that future implementation of negative emission technologies will let us pull the CO2 back out of the atmosphere. This is problematic for a lot of Earth system components that are not perhaps able to rebound rapidly in the way that, even if the surface temperature rebounds, not all Earth system components will rebound in the same manner. So the first problem with an overshoot scenario is that, to begin with, the permafrost will drive further warming. So the overshoot will be even higher than what you might have counted with, and you end up overshooting a lot. The second problem with combining overshoot warming and permafrost thaw is that there is going to be a large amount of irreversible permafrost loss, where once you've thawed the permafrost and triggered perhaps the abrupt thaw collapse into a lake, even if the temperature goes back down, the soil is not necessarily going to refreeze again, because you change the whole properties of the landscape. You change the thermal properties, you change the hydrological drainage, you change a lot of things. So there's a strong element of irreversibility to this. And this is also bad news when it comes to projected emissions, because this actually translates to really strong increases in projected emissions from permafrost. Now, again, we're seeing combined emissions, and I also want to emphasize that it says gigaton CO2, but it's CO2 equivalent. So here we include the methane converted to CO2 equivalents using the 100-year timeline calculation factor. And you see here the difference between no overshooting by ½ degree and overshooting by 1 degree is unfortunately very substantial. So this, you know, if we think of a potential scenario, future scenario where we have very strong activation of abrupt thaw and potential overshoot, the permafrost carbon feedback will actually eat up a very large part of the remaining CO2 budget. The last IPCC report, Working Group 1 AR6, they did account for the they did an estimate of the permafrost carbon feedback. It didn't fully account for all of the abrupt thaw mechanism. So if you add abrupt thaw and potential overshoot, you actually end up with the situation where the remaining carbon budget, as calculated by the IPCC, might be a lot smaller just due to these permafrost carbon additions. Especially at the 1.5 degree carbon budget, it's a massive potential decrease. Also for the 2 degree warming budget, this of course has a big impact, but less immediate. And so another important question then, as also asked by the IPCC report, is that thinking about overshoot scenarios, could climate change be reversed by removing carbon dioxide from the atmosphere? This is also material from the Working Group 1 report. So if you have a scenario that looks like this, with a very pronounced peak in CO2 that is then drawn down again, their answer is that yes, surface warming can be reversed, but there's a lag time of a few years. So you see a global surface temperature change rebounds relatively quickly, and in this scenario stabilizes at somewhere around 1.4 degrees over pre-industrial. So lag time of a few years for temperature, and then they state that, okay, also permafrost is reversible, but with a lag time of decades. I would actually argue that the models might be overestimating how quickly permafrost area would rebound, and I would say that it might be closer to a century, but I guess that that's my interpretation. But still a very substantial lag time. And then if you move to other Earth system components, for instance, ocean thermal expansion, there are lag times of centuries to millennia, and basically it's not reversible. And this holds true for a lot of other very, very important Earth system components. But then I want to actually bring us back to the permafrost one. And okay, so we do have a reversibility in the permafrost areal extent. But one thing that is very important to note here is that we still have a permanent loss of several million square kilometers of permafrost. And all of those million square kilometers of permafrost will altogether contain several hundred gigatons of carbon. And that carbon is, we just start scratching at the surface and the microbes start decomposing it, but it actually will emit carbon for several hundred years. So even if the extent bounces back largely in a few decades, this area that's thawed will keep emitting for several hundred years, no matter what we do, unless we really cool the climate a lot. So there's also a sort of intergenerational justice component to this, in that the permafrost once thawed will keep emitting. And we are actually binding several future generations of humans to have to use continued negative emissions to just compensate for the carbon that is constantly being lost from this permafrost that thawed over a few decades. So that is something that is really important to keep in mind, is that part of it is still not reversible. So closing remarks. The IPCC has found, and supported by a lot of methods, a lot of models runs and other scenarios, that natural carbon sinks are projected to weaken, but it really differs with different emission scenarios and dynamics. But this is still important to keep in mind. And EHSMIP 6 generation of Earth system models lack a lot of important long-term feedbacks, including the permafrost. I didn't talk so much about this, but the models that went to EHSMIP 6 did largely not include the permafrost carbon feedback. There are a lot of Earth system models that do a really good job with the permafrost carbon feedback, but they just were not, in many cases, the version of the models that went to EHSMIP 6. And likely, permafrost is not a global scale tipping element with a single abrupt threshold. But there are abrupt thaw processes create strong local scale tipping points and greatly increase warming. And we also note that overshoot warming will trigger, if it happens, irreversible permafrost thaw that drives additional warming for centuries even after the climate stabilizes. And permafrost potentially reduces the remaining CO2 budget, perhaps by as much as half for the 1.5 degrees target, if in a scenario with strong overshoot emissions. And global warming, or the surface warming itself, is reversible by removing CO2 from the atmosphere, but many feedbacks will persist for centuries to millennia. So it's really important to keep that in mind when you sort of plan for those different safe landing climates. Okay, thank you all for listening.
Great. Thanks, Gustaf. That was a really excellent talk, and nice to hear from you. So I think now we'll start off our question and answer session. And so I think we can start with a question for Gustaf. Could you talk a bit more about permafrost and tipping points in Earth system models? So to what extent is permafrost and the landforms that we need, how far are tipping points built into existing models in the IPCC? And do you think this causes a problem, and why we may not be seeing an exponential increase in CO2 emissions in response to temperature?
Yes, I think that's a very sort of big and important question, and I might bounce some of it over to other experts like Victor. But I think so in general, to EHSMIP 6, so the collection of our system models that was used to create a lot of the background material for the last IPCC report, largely permafrost was not included at all, not even the gradual permafrost thaw. A few, I think 2 of the land surface models that were included had gradual permafrost thaw activated, but I don't think that many others did. So the IPCC Working Group 1 report still actually quantified the permafrost carbon feedback based on meta-analysis or compilation of different earlier modeling runs. So it is, I think it's actually really well treated in the last IPCC report, especially in relation to earlier models or to earlier IPCC reports. So it's calculated, but not from the models, but rather from earlier studies. And then there are a few Earth system models that are approaching the capabilities to really represent abrupt thaw or local tipping points by starting to build in different landforms or massive ground ice in the model, and actually dealing with this either as an explicit physical process or as something that you can parameterize as a function of how much ice was there. But I think this is really challenging, because if you really want to get to a model that can build the ground ice, you really need to have the model run over a very long time. So you need to have a model that starts at before the last glacial maximum and then builds all of this ground ice over time to then have a decay. So I guess an approach where you can observe the ground ice distribution and landforms and parameterize that into the models, prescribe it so that the models can use the data is a more reasonable approach. I don't know if Victor has or someone else has more comments on that.
Yeah, I can echo your points that yes, Earth system models which we used in the IPCC there were only few, which include permafrost and even less permafrost carbon. So that's definitely something we can pick up for the next IPCC report, but also in this EHSMIP project, because we can also prescribe permafrost carbon emissions from offline models. I think that's possible. Yeah, and of course, when we initialize the model, I think it's too early for any ESM to do runs through the glacial cycle. So we actually rely on your data, Gustaf, to initialize the model at present day, because it's really hard to get the whole history. So that's why your work is so important. And yeah, if I may continue, I want to shoot also some questions from the Q&A, and one of them was, I think, to Hanne, and it is about remote sensing. So to what degree are there ways to measure and monitor large areas of permafrost and its change from satellite images, so using radar probes with helicopters? So to what degree is it possible?
So this is already, of course, done. And I think that you saw that the map I showed you today is actually a modeled map. And that means that it builds on doing exactly that by actually recording the ground surface temperature. And then, of course, using the relationship between the ground surface temperature and the expectations for permafrost in the ground. So that's one thing. And the other thing is that I also showed you today that by using INSAR technology, you are actually also able to observe the movement of different landforms, a little bit depending on the size and how they're configured and so on, but it's possible to go in and use remote sensing. And I would say this is not something that we would even have been dreaming about doing maybe 15 years ago. So now we're starting to have tools and technology that can actually start to address things at the landscape scale. Having said that, we also understand that there's quite large variability even within one rock glacier and how it actually is moving. So the resolution is, of course, the next thing. How good data can we actually get? And then the next thing is the accessibility. And I know that, for instance, in Norway, we have a very high rate of accessibility to INSAR. There's like an open database where you can actually go and look at anywhere in Norway and see how the ground surface is moving. And that isn't the case, for instance, in Svalbard, and most other Arctic areas, you don't have directly open access to that yet. But I'm sure this is the way things go, and this is going to be important, and it will change the way we observe permafrost landforms for sure.
Great. I think our next question is also to Hanne. Could you talk a bit about what controls interannual variability, both in the active layer thickness and also for the borehole temperatures that you observe in Svalbard and potentially other places?
Yeah, so mainly what I've shown you is a site in the Arctic that really has undergone extreme warming. Up until 2015-16, we had a very, very quick increase, and I showed you temperatures on that. And then since then, we have had a small decrease in temperatures, and that's mainly driven, I saw many ask questions about that, that's mainly driven by air temperature fluctuations. So most of the landforms, they respond quite quickly to that. Mainly, of course, if you're dealing with a borehole in rock, that is going to do it much quicker than if you have a borehole that is sitting in a landform with a thick organic cover, such as the ice wedges that I also showed you. They have less direct response to that. So this is one of the things. I saw a question which was about how does the change respond to the depths of zero annual amplitude, and we don't actually look into that. We use the active layer as the ECV, so the essential climate variable, because that is so important for the ecological system. You need to understand the thickness of the active layer and its variability so that the top permafrost is the really vulnerable part. And with the top, I mean the top meters, it does take time to thaw permafrost, as also Gustaf showed. And therefore, that's basically what we're interested in. But when we want to observe long-term effects on permafrost, it's important to come below these 10, 20 meters so that we're actually seeing the result of longer-term climatic variability on the permafrost. And then the temperature profile that I showed you, the trumpet curve, as we call it, it is a very kind of textbook example, because of course normally they would change and you would be able to see how a warming site will not have a straight line but would actually be turning towards a warmer condition and so on. So that's basically how we use the ground thermal regime and the data and try to look at them that way. And the data I showed today is just a very basic way of looking into the data. You can of course go in and actually look at and study what is happening to the shoulder seasons. Do we have longer periods with active layer? And if so, then we have longer periods where we have activity in the ground for slope stability and so on. So that's quite a lot of things that one has to consider when it comes to dealing with the observations of the permafrost temperature. But now I think I'm moving far away from what many of the questions were, sorry.
Great, thanks, Hanne. Just a reminder to put your questions in our question and answer box rather than in the chat. I think there might be a couple of good questions in the chat that we will lose forever. All right, Victor.
Yeah, I just want to continue with carbon questions, in particular on the abrupt fall for Gustaf. So there is general interest. So if you want to have models doing local tipping well. So what are current models missing? So what processes should we include, or should we try to represent more adequately to capture abrupt fall?
I mean, I think as I mentioned, there is there are models that are already starting to become able to do this, and I think as a field, I mean, I'm at least from the beginning very much a field scientist, and I think field observation scientists, we always like to make observations and then we write in the conclusions that, and this has to be implemented in Earth system models because it's very important. And I think here we are actually approaching, at least for if we want to do this across the Arctic, I am worried that the models, the models will get there before we actually make maps that are really good enough to make it work. So I think that we are lacking observational data on the spatial distribution and amount of ground ice that, we have data, but I don't think it's synthesized well enough. And another really important part in this is to be able to tell the models more specifically the soil properties locally, because the difference if you have peaty horizon, like a horizon of peat or organic soil at the surface, or if you don't have that, it makes a world of difference, and it makes the thermal properties of the soil is completely different. So data set, observationally driven, observational data sets of ground ice and ground properties to really to prescribe into the models is one thing that we critically are lacking. And then I think that when it comes, from the modeling side, my understanding is that to really model this mechanistically, you need to have models that where you can deal with the ground surface moving, or where you can deal with actual changes in topography and routing of water within a grid cell. So this is something that is solvable computationally, but I think it's quite a challenge, and I think that depends a lot on how the model is built from the first place, and different models do it in different ways. But I think that is one of the big computational challenges in how these fine changes of how water moves and all of that, because that water also is so important for the thermal, where the water, where the heat energy goes and how much the permafrost can store. So these fine scale things need to be solved in a smart way computationally, but I'm quite, from what I'm seeing in papers coming out, that is already happening.
Yeah, thank you. And there was also a link question on vegetation dynamics and perhaps also fires. So do you think is there a chance that we get them right in the models?
Well, that's a good question. Completely. Obviously, vegetation dynamics are super important, and there's so much, so much that controls vegetation, including nutrient dynamics, not in the least. And I think that's also, there are a lot of things that I never touched upon, but there are good indications that a model that perhaps has a tight and well implemented nitrogen cycle, where there's nitrogen limitation of microbes and so on, gives a very different response of the permafrost system as a whole, because it might be that the future microbes will be nitrogen limited in a stronger way than we thought before. So that is one example of, I think, very interesting dynamics. Root dynamics, and how root dynamics will change, also including priming, where the roots might actually exude carbon compounds that actually make the decomposition go faster. It's another interesting dynamic. But the fires are certainly extremely important. Also something that I didn't touch on, but I mean, the fires have a really strong direct impact. You burn a lot of biomass. I think the fire years of 2020, I think the Arctic fires directly emitted more than all the Nordic countries together. But one of the other things that we have the short-term impact of fires, but then you also have this long-term impact where the fire burns away the surface soil layer. So the insulating, the peat that actually protects the permafrost is burned away. And also the tree canopy, perhaps if you're in the taiga, disappears, which actually makes the heat penetrate much faster into the soil. And you also have a long-term effect of permafrost thaw after the fire, which can also drive even further warming. So I think the fire dynamics are also very important for the models.
Thank you, Gustaf. We'll try to get that into models. Claire?
All right. I think our next questions are about feasibility of the 1.5 to 2 degree target warming to Gustaf with permafrost carbon.
Yeah, I mean, it's still it's still physically possible. I think that all of the the possibilities are still there. With the physical climate system, even including the permafrost carbon feedback, it is still physically possible. I mean, beyond that, it's obviously a policy and politics question, but it's definitely still within the realm of feasibility. And I think the trajectories that get us there all include rapid emission reductions in the coming 10 years. We need to reach net zero 2050 or even earlier, and then after 2040, 2050, there needs to be strong negative emission implementations, or some at least negative emission technologies working. And I think those are the scenarios that get us to 1.5. The IPCC 1.5, special report on 1.5 degrees did account. They did account for the permafrost feedback in at least in a relatively robust way. So I think that I still think that the looking at the scenarios in the 1.5 degree special report is still quite okay, even if the permafrost feedback might be a little bit stronger than what they accounted for. It's not that far off.
Thank you, Gustaf. Just want to pick up a question for Hanne. Svalbard is strongly influenced by vicinity to marine environments. How does this influence warming rates? And in general, in the coastal area, how is permafrost affected? Does it fall slower or faster than in the continental areas?
Yeah, I touched a little bit upon it, showing you the difference in ice wedges. But of course, Svalbard is kind of the extreme, that it's this warm. It's also the part of the high Arctic where we have the warmest permafrost by far, because we're sitting in the middle of the sea. And we see very clear effects. For instance, if we have very cold winters where we have ice on the fjord you see behind me is, coming all the way to the settlement and where we have our research site. So of course, the influence of the sea is very big, but and of course this basically means that we have a situation where the variability is a winter variability. It's not a summer variability. It's very, very difficult to have variability in the summer in the sea that way. But in winters, because of sea ice extent varying, we can certainly have some variability. And this is, of course, important when we talk about permafrost, because permafrost is where we are really dealing with winter landforms that way. I would say that we are right now seeing also in permafrost a strong focus on what's actually going on in the coastal zone, of course, because most people live there. So it's important to observe that coasts, both maritime, but also in continental areas, they can then have variabilities in how they respond to changes as well.
All right, one question to both of you. Could you say something about submarine permafrost and carbon stocks under there?
I can maybe start by saying something about submarine permafrost, and then Gustaf is probably better in talking about the fluxes. So the interesting thing about permafrost in the sea is that most people don't actually think about it. If you look at a permafrost map, many of them don't even, they just have sea. But when we know that we, during glaciations, have actually a lowering of the general sea level of about 120 meters, this exposes a large part of the shelf, which then actually develops permafrost. So we know that we have permafrost, for instance, widely developed in the Siberian shelf. So there are large areas where permafrost have then been kind of put into the sea as sea level rose when glaciers were shrinking. And then that becomes a possibility for thawing, and then you can also get release of greenhouse gases from there. Am I right, Gustaf?
Yes, you are. I mean, there is certainly, as you mentioned, a lot of subsea permafrost. I think the subsea permafrost is roughly 1/10 of the terrestrial permafrost surface. So if it's 2-3 million square kilometers, I think, I'm not entirely sure. It's a really complex system as well, because it's a mix of old terrestrial soils. So it used to be under, it developed, the permafrost developed under air. It didn't develop under the sea, and it was later flooded. But there's this mix of old terrestrial soils overlayered by marine sediments that are then, been accumulating on top of them. And there are also, in some cases, several layers, because the sea, there was, the sea came up and went back again during repeated glacial cycles. And altogether, this permafrost system, subsea permafrost system, holds a lot of carbon. It's believed. There's very limited data, but there are even publications suggesting that it holds almost as much carbon as the whole terrestrial permafrost system.
We can maybe say that there is a few scientists that have actually tried to access this by drilling into the sea, and this is an extremely complicated operation, of course. But there are measurements, and there is also papers of release of greenhouse gases from the sea, and that's of course the pock marks and so on. That's of course why we know this is happening. Yeah,
and there are another added complexity with measuring the fluxes from the. It's that you have to separate. There are seeps of geologic methane, so more like from natural gas fields, etc. And then there are the methane hydrates, which is a type of, a sort of stabilized gas form that is specific to areas of high pressure or low temperatures, that is found along the coastal shelf seas. And then there is also fluxes from normal degradation of organic matter. So these three sources of greenhouse gases also need to be separated and sort of kept track of, but there are indications that there, some of those systems are already being activated and might start to release even more greenhouse gases.
Yeah, so Gustaf, if I can follow up on that question, how can we actually observe in the present day if we're losing permafrost carbon?
That's really another type of data I didn't get much into or talk about much is, of course, flux data. So people that measure ecosystem fluxes. It's one of a big community of researchers, and I think one of the most important data sets, types of data we have available to us to study this. And that is being done all across the Arctic in different places using different methods, from small chambers that you put on the soil and measure, you measure CO2 or methane or nitrous oxide production or oxidation in the soil. You also have towers called flux towers, eddy covariance towers, that can measure over larger footprints. You have a network of very tall towers that you can link to airplane observations and really model how greenhouse gases move through the atmosphere and how they either are sourced or synced from the ecosystems. So there are all of these observations, and there are long time series, and they are really fundamental data sets for us to understand the greenhouse gas balance. So like most of I showed you some examples of models or synthesis of different landforms, and to really understand what a lake or a thaw slump or whatever, thawing permafrost, how that responds to climate change, we've really tapped into usually decades of flux measurements done by field scientists in different areas, and then compile that over different areas and analyze it together in a sort of a big way.
Yeah, thank you, Gustaf and Hanne. Just wonder, we are coming slow to end, but we have not talked much about geological evidence of permafrost tipping point. So how much can we tell about whether permafrost carbon can really increase atmospheric CO2, or whether you see on geological, on physical side, that permafrost is really affected or affecting the climate system? So from the past geological records.
Are you thinking about like cores or something like that?
Yes, we only have cores. We also have ice cores. I think ice cores are our best archive, but boreholes and other. So how abrupt can be this permafrost changes, and which you record in the past, because in the past we also have abrupt climate changes.
Yes, I can only say that we have very few permafrost cores that really go this far back in time. It's extremely expensive and difficult to core really deep into the permafrost. So typically the best evidence we have for old permafrost doesn't come from cores. It comes from exposures where you have slumps and slides. from deep holes in the permafrost where you can actually understand some of the variability. I have not seen any publications that really document how the CO2 or have been able to reconstruct how greenhouse gases vary through geological time in permafrost yet. And that, I think, is because the way, the ice core people, they have done that because they focus on this for the glaciers, but we have not yet come to that point in permafrost science, which I think is really going to be, it could be super interesting. But having said that, it's a lot of local factors that affect the drill site. So you have to choose your drill site very carefully, and you probably need more than one. So you need to actually have a few sites that you would spend some time thinking about, why do I measure in these sites? It could be a list site where you have a long record, and therefore you might be able to actually see how the changes are affecting permafrost this way. But it's an interesting thinking, and I think that it's the right way to go.
Yeah, I can just comment to follow up on that. Like if you look in the ice, so we have ice core and other records of how atmospheric concentrations of CO2 and methane has changed over time. And I think looking back, for instance, at the last, when we came out of the last glacial maximum, we had a situation with Hanne showed this map of a lot of large ice sheets, but also a lot of permafrost, and reconstructing what happened to the permafrost carbon as we came out of that cold period and into the warmer interglacial suggests that several hundred gigatons of carbon was moved from a frozen state into other types of soil. So we reconstructed the carbon pools then and then now, and then we see that the carbon, there's roughly the same amount of carbon in the system, but it's in completely different places. It's not necessarily frozen anymore. We had these northern peatlands that grew over the Holocene, so there are examples, I think, quite strong paleo evidence of large shifts in these carbon pools in the past. And I think Claire's work on reconstructing peatland dynamics both before and after the last glaciation, showing how also landforms such as peatlands can really change dramatically, and the very large fluxes of carbon would have been needed to really change the carbon pools that much. So I think that there is at least some literature suggesting that perhaps the ocean wasn't the only dynamic carbon CO2 moderating buffer in the deglaciation period.
Yeah, so if carbon went from frozen state to a peatland form somewhere else, then on between it may enter the atmosphere and
exactly.
influence climate. So
it must have come from, to come from Yedoma in Siberia to a peatland in the West Siberian lowlands. It must have been in the atmosphere for at least a few hundred years in between, or 1,000 years. So definitely it has moved around.
Yeah, that's exciting. So we approaching now the end of our webinar, but and you can find just for our speakers, you have still quite a number of unanswered questions. You can just also look at them, and they are also in the Miro board. Just for wrapping up, I think we wanted to also to remind you about the Tipping Elements Intercomparison project, so TIPMIP, and since we are discussing permafrost, which also affect the carbon, so it will be a great question how we can put this permafrost effect of feedback through carbon on climate. And yeah, Caroline just put a link into the chat box to the TIPMIP.
Yep, and there's the Miro board, so that will stay open for the rest of the week. So please, if we didn't get to something or you're interested and want to keep discussing, that's a great forum to use.
Yeah, and also as a reminder and just an outlook, the next webinar in this series will happen next Tuesday, so just in a week from now, and we will focus on ice sheets, and it will take place exactly on this time on Tuesday, January 25th. with speakers Sofia Novicki and Ricardo Winkelmann. And the link to register will be also added to the chat box. So it's already there. I think Caroline put that. So that will be also next interesting event, also about cryosphere.
Great.
So.
Well, thanks everybody. Thanks Gustaf. Thanks Hanne. Thanks Victor.
Thank you, everyone.
Very nice.
Thank you very much.
The speakers. Yeah.
Thank you.
See you. Bye-bye.
Bye.